This method of integration is a simple method which states that if a variable of a function in an integration substituted or put by another variable, then we have to take differentiation with respect to new variable. As here this is a function of x and we are going to differentiate it with respect to x. If we put x in term of t in function, then we have to differentiate with respect to t, and value of integration does not change because integration of f of x dx is equal to integration of f of t dt. Now, when we use this method, as we know there are limited rules in integration, so we have to simplify integration to evaluate. As we know, for composite function f of g of x, we have chain rule in derivative. Now, in integration, what to do? If f of g of x is given such a way that such a integration contain g of x, a derivative of g of x, g dash x into g dash x in integration, then we can use this method. This is a method in which we put g of x is equal to t, that is in composite function term of x in term of new variable t, and differentiate with respect to x so that we get g of x, derivative of g of x, g dash x, and t with respect to its dt by dx. Now remember, we have to transfer dx on left hand side. So whenever we use this method in example, we always take derivative of term of x multiplied by dx, and derivative of t with is dt. Okay, so g dash dx is equal to dt. Now this integration in which f of g of x is a composite term in which g of x is replaced by t, so it becomes f of t. And now observe, g dash x dx, this derivative operator is put by dt, so we get integration of f of t into dt. Now value of integration does not change, as this is value is given value is I, so new integration has also value I. Now integration of f of t, as we know integration of function is represented by capital, so f of t has integration capital F of t. And remember, we have to resubstitute the term as we asked integration in term of x, so we have to evaluate integration in term of x only. So final answer will be, by resubstituting t in term of x, f of g of x plus c. And logarithmic and inverse trigonometric function has no standard integration, as we seen in formulas of integration. So whenever the terms of logarithmic or inverse trigonometric function, we have to use substitution method for to evaluate integration. Substitution method we solve this integration. Now observe, in integration we have term sine of e raised to x into e raised to x dx, while composite term in integration we use this method usually. Here sine of e raised to x is a composite term, is in form of sine of f of x, and you know its derivative. Now in integration, in composite term, the term of x in here in this term, x is a function of e, exponential function, so here term of x is a e raised to x, so we put e raised to x. If we differentiate this with respect to x, derivative of e raised to x is a e raised to x, and we know this is term of x, so it multiplied by dx, and dt has the derivative dt. These two terms are put in integration, then the value of integration does not change. So I get again I is equal to, on left hand side, integration of. First, by identifying composite term, we put substitute the term of x in that term. So e raised to x substituted in sine of e raised to x, so it becomes sine of t. And now remaining terms are in relation of dx and dt. Now here is a term of dx is e raised to x into dx, which is equal to dt, so I put it as a dt. See, this is a term of x and integrated with respect to x, which is a given. Now by substitution we convert it in term of t and integrated with respect to t. Now integration of sin t, as the integration of sin x is minus cos of x, similarly integration of sin t is minus cos of t plus c. And remember, always resubstitution is necessary, as we asked integration in term of x, so final answer should be in term of x only. By resubstitution t in term of x, which is e raised to x, we get minus cos of e raised to x plus c. Similarly, we can solve the remaining example. The next example is e raised to tan of x into sec square x dx. Now observe here. Here e raised to tan x is a composite term as it is in form of e raised to f of x, and sec square x is also composite term as it is in form of f of x bracket square. But as we put term of x in e raised to tan of x, that is tan of x, its derivative is a sec square x. So we can get here derivative of term which is a suitable to substitute. So we put here only tan of x is equal to t and take differentiation with respect to x. Derivative of tan of x is a sec square x with respect to x, so we multiply it by dx, and derivative of t is a dt. Now integration will become, therefore I, always remember on left hand side the value of integration is remain constant in substitution method, that is I. So I is equal to integration of e raised to tan of x is a t into sec square x dx, which is a dt. So if we define composite term, then put term of x in that term. So e raised to tan x is substituted by tan x is equal to t. So it became e raised to t. Integration of e raised to t is always e raised to t plus c. By the substitution t, value of t is a tan of x is our final answer. And this you can solve the remaining example as well. The next example is a sin cube x into cos of x dx. Here simple is that there are terms, but sin cube x is a composite term which is in form of f of x bracket cube. So power functions variable is replaced by trigonometric sin x function. So we can put sin x as it has a derivative cos of x which contain in integral by differentiating. But see the method. The method is similar to each examples. We put first term of x in term of t and take its differentiation. Here it is a cos of x dx is equal to dt, and which we put into integration. So the value of integration does not change, it remain I on left hand side. And now identifying the composite term in which we substitute term of x, as here sin x is a term of x, though sin cube x is a composite term, it will become t cube, and remaining term of dx are in relation of dt. So here cos x dx is equal to dt, and now t cube is a power function, its integration will be t raised to 4 by 4 plus c, and finally the substitution term of t, that is sin of x raised to 4 divided by 4 plus c is our final answer. And last example you can observe, here we have to put x square and derivative of x square is a 2x, so it will become cos of t into dt, which has the integration sin of t, and so finally we have the answer sin of x square plus c. These examples contain the function of the function which are only differentiable, like logarithmic function and inverse trigonometry function. The first example, as we see, sin of log x is a composite term. As we know, we have to put differentiable functions always. So we put log of x is equal to t. So its differentiation with respect to x will be 1 upon x into dx is equal to dt. So I is integration of sin of log of x is equal to t, and 1 upon x dx is equal to dt. So integration of sin t is a minus cos of t plus c, and finally we resubstitute the integration in integration term of x, that is t is equal to log of x plus c. So similarly we can solve the remaining example. Next example is I is equal to e raised to tan inverse of x divided by 1 plus x square. Learn how to observe how the terms, how the steps are taken. Here we have to put tan inverse of x, as it is a only differentiable term, so we have to differentiate with respect to x. Its derivative is 1 upon 1 plus x square dx is equal to dt. Now I will integration of e raised to tan inverse will substitute by t, and remaining term of dx is equal to dt. Integration of e raised to t is always e raised to t plus c, and finally we get e raised to tan inverse of x plus c. And last example, you can observe that you have to put here sin inverse of x is equal to t, which has the derivative 1 upon root of 1 minus x square. By simplification we get the integration in term of t cube with respect to t, and integration of t cube is t raised to 4 upon 4 plus c, and finally resubstituting the value of t, you get the answer.